The theorem on the screen is the so-called Coarea formula, and the series that we are currently inside has been devoted to a proof of this theorem. After some building up in previous videos, which also of course touched upon many other concepts, we are ready to give a full proof of this amazing theorem due to Fetter originally. Okay, we begin with the recall that differentiability of the function f is a consequence of Rademacher's theorem. And part of that theorem also tells us that the derivative is a measurable function, and because this Coarea factor continuously depends on the linear operator, in this case dfx, it follows that this Coarea factor dfx is measurable real valued function on Rm. And this will make the left-hand side of the quantity, the claim, actually valid and well defined. The next simplification that we had was that, and this was done in video 5, where we talked about justification of why Coarea factor has to be what is here. And in that video, we saw that it suffices to prove the Coarea formula for any L1 measurable function. It suffices to prove it for just characteristic function of measurable functions, which is equivalent to saying that for any measurable subset of Rm, integrating the Coarea factor dfx on the set A is the same as first integrating over the fibers, but when you integrate this characteristic function over fibers, you get nothing other than m minus n dimensional Hausdorff measure of the level set intersected with A, of course, d, l, n, z. So if we prove this, then we will have the full version by approximating arbitrary g with summation of characteristic functions. The next thing we have checked comes from our video on Coarea inequality, and that says that if A, a subset of Rm, is measurable, then this quantity y being mapped to the hm minus n measure of f inverse z cap A is ln measurable. Sorry, here I mean z. Which makes the right-hand side here well defined, because now we know it's ln measurable function. And this interestingly required the Coarea inequality. The idea was that if A is a compact set, this is pretty routine, but for arbitrary ones, we want to approximate A with countable union of compact sets up to a null set, and there's no other way to deal with that null set other than the Coarea inequality. So in those videos, we go over all details of subtleties of why we need a Coarea inequality in the proof of Coarea formula. Okay, so that was number 3. Point number 4 now will be that we need to prove this star, and then it's an observation that either side of star is additive, countably additive in the set A. In other words, if you have A1, A2, and so on, countably many, then integral over union of AI, and if these are disjoint, which we can always fix by removing the overlaps inductively, of this Cn dfx, obviously you're integrating a measurable function over disjoint union. You can just do it separately on individual ones and then add them up. So dlm over I. So that is true. And the same holds for the other side, that integrating hm minus n f inverse of z cap this set union over I of ai dln will be the same as summation over I of integrate over Rn hm minus n of f inverse of z cap individual ai dln. And this one follows basically by set theory, because AIs are disjoint and the intersection of the level set with their union is union of its intersection with individual ones. And what do we conclude from this additivity on both sides? It is enough to decompose A into a countable union of subsets of sets for each of which star holds. It means we can work in pieces. It suffices to do on tiny bits of your measurable set A. And here we begin doing this subdivision. So the first subdivision we do will be, we write A equal to a null set. So there could be a null set which is, for example, the set where the function f is not differentiable. Then there is A0 and then there is A1, where A0 is the set where the derivative exists, but rank of the derivative of f at x is equal then n. I mean x from A, so that you're within A. So an A1 will be those x's in A where rank of the derivative equals n. And these three sets are disjoint. They have empty intersection. Therefore, it suffices to prove star for individual ones. So star, which is the Coarea formula, holds on n. Okay, so we integrate over n characteristic function dfx dln x. This Coarea formula, I'm sorry, not characteristic function, but the Coarea factor, is not even defined on this set, but because we're integrating over a null set, it's always 0, by agreement, for example. Then we have m minus n f inverse of z intersection with n dln of z equals 0. Okay, this one was easy, just definition. This one here, though, is not an immediate fact, as we have been talking a lot about. It follows from the Coarea inequality, which allows to deal with the null sets n. Okay, so that takes care of it. The Coarea inequality, the formula, holds on A0. Again, this is not trivial. The integral over a0 of the Coarea factor equals 0 because of definition of Coarea factor. And if rank is strictly less than n, that Jacobian vanishes. The fact that this other side vanishes, again, is highly non-trivial. And that is what we call the weak Sard type theorem. And we gave a proof of that as well. That will be in video 7. Okay. We gave a direct proof by covering arguments that on the critical set of the function f, this integral of fibers, measure of fibers vanishes. Okay, so it remains to deal with the regular set, with set A1, which was, again, x is in A, where rank of derivative of x equals n. And also the previous points tell us that, in fact, this is the only set which probably contributes to either side of the Coarea formula, any quantity other than 0. If this set A1 is a null set, that's the end of the story. Again, we apply the Coarea inequality, we're done. So we will suppose that A1 has measure 0. Okay. Because otherwise we're done. Okay, what was our tool to attack this set? What was the main theorem that we discussed? That was the so-called implicit function theorem for Lipschitz functions. In video 4, I went into the details of this. What we had proven was a lemma which said that under these conditions, so A1 is a set of positive measure, rank of the derivative is equal to n on that set, then the claim was that there exists a subset of A1 with positive measure. That means it's still a significant set and not just a singleton, for example, such that on this K we can iron out the fibers of the Lipschitz function f. So I like to have some clean pictures here. Hopefully, I'm not really good with them. So of course I cannot draw a measurable, arbitrary measurable K. So I for illustration purposes at least, I want to draw an open set. This fiber also doesn't have to be even connected, but again, I draw a cartoon only. Okay, so what I have here is, okay, I begin with f, of course. That is my original Lipschitz function, which maps into Rn from this subset of Rm. And a fiber of the point C that I've drawn in blue is just any subset. It is not even a manifold in general. But then there is this K, such that things are a bit better on that. I can find a C1 diffeomorphism. So there exists C1 diffeo psi on an open set, okay, from an open U. Well, I don't want to add too much notation. On an open U, on an open set containing this K. So K is inside some larger U. which I don't want to draw to keep my picture simple. And then I transfer everything by this psi to another copy of Rm, so that now the fibers become exactly subsets of the vertical Rm minus n. So let's do some labeling here, that's important. So here will be Rn, and m is bigger than m, so here remains Rm minus n. Okay, so I do this, and then there's even more true here, that this composition here, which is f composed with psi, satisfies this. Composition of this applied to any point xy is only a function of x. Okay, so this becomes phi of x, where phi is particularly nice. So phi is by Lipschitz, and C1 on an open set containing all the relevant parts. So this will be projection of, okay, let's call this K tilde, the image or pre-image of K, because psi is a by Lipschitz C1 diffeomorphism, it has a C1 inverse. We can even identify K and K tilde. So K tilde and K are just the same under the identification psi. So this will be projection of K tilde onto Rn, the orthogonal projection. So phi is defined on an open set. It is a C1 by Lipschitz function. And then our function f, after this change of coordinate system in the domain, our original Lipschitz function f becomes just this phi. And that is the whole idea behind our proof of the Coarea formula, because now we want to deduce the Coarea formula from Fubini's theorem. Okay, now this looks better. Let me do some cleanup. It will give you some time to think about what's going on here and why things become so much nicer after this change of coordinate system. So such that there exists some psi C1 dpho whose image, say, which is an open set, contains K such that, yes, such that this last one. Okay. The last technical thing we need, and we covered it in our study of the linear algebra behind the Coarea factor, was a change of a chain rule for the Coarea factor. So from this formula, let's call it formula double star, we already had star, derivative of f at psi of xy composed with derivative of psi at xy, that's just chain rule of derivative, is derivative of phi at x. That's just chain rule of derivative. Then we saw the Coarea factor is a bit trickier because it goes between, it involves maps between non-equal dimensions. What we proved was that the Coarea factor of derivative of f, that is the original function, computed that image of psi. So this is xy here. So here is psi of xy is equal to the following. So you get derivative of psi at xy and determinant of this. So that is not surprising. It's the Jacobian of change of coordinate system. The Coarea factor of this revised map. But then there is this important part that comes in. So this will be determinant of restrict psi to just the vertical fiber. So that will be the blue vertical line in my new domain. Now that's a function defined on a copy of, on a subset in Rm minus n. So it has it's C1, it has a derivative and its determinant is computable. So equal to that. Let me just, to save some notation here, replace these xy's with this. Okay, this may look a very lengthy formula, but that will be very important to help us reduce to Fubini's theorem. In fact, from this point on, it's just computation using Fubini's theorem. So I want to compute the integral of the Coarea factor of original f of x. I don't want to put x because I want to reserve it for some other notation. So this is the original left-hand side rather, that we want to compute. And I'm working in the original domain k. But now I can do a change of variables formula, a u substitution, and transfer that integral into k tilde region. What happens is just you pull back the function, so this will be df computed at phi of xy. So every point is a phi of xy for a unique one. But then there will be the determinant of the derivative of psi at xy. That is the Jacobian. So I underestimated how much space this will take. So let me see. So I'm doing a change of a u substitution, a big one rather, to transfer an integration over k to this. So this will be determinant of that, dlm now xy. So my rm is now, the variables I've chosen are xy. I hope this didn't confuse you. Xy here, x is an n-dimensional vector and y is an m minus n dimensional, so that they add up to m variables. Okay, so this is just a u substitution of integrals. Now I want to apply this last formula here that we had. When I multiply both sides by determinant, then I end up with this. So this will be Coarea factor of f o psi computed at, so what I mean is the derivative of that function. So Coarea factor of d of f o psi computed at xy, and then absolute value of determinant of d psi restricted to the fiber above x computed at xy dlm of xy. Now I use Fubini, and that allows me to integrate first over the projection of k tilde onto Rn, this horizontal projection. That may be a confusing term. Projection onto the horizontal space, or Rn. And then this will be integral. Now, so this will be dln x. So let me go back to my picture to explain this. So I'm integrating over here. I can freeze x, integrate along y, and then integrate, add up with respect to x. So that's Fubini. So then I want to integrate, so freeze x, integrate with respect to y. So this will be in m minus n dimension. And this will be integrate over x times r m minus n. All of these, of course, just the part that concerns k tilde. Now I want to copy paste this verbatim, x times r m minus n, computed at xy determinant. Now for this one, we have actually a simpler quantity. Fo psi is just this function phi. That's the double star formula. So its derivative is just derivative of phi, and its Coarea factor is just the usual Jacobian of phi, because phi is between equal dimensions. And once you look at the orthogonal complement of the kernel of a linear map, whatever you get for the usual determinant is exactly the Coarea factor, because you're looking at the orthogonal complement of the kernel. And here, of course, kernel of dFo psi is the vertical line. So this will be just d phi at x, determinant absolute value. Now comes the observation that this quantity is independent of y. So we can put it outside the inside integral. Therefore, we end up with just integrating this quantity. But what is that quantity equal to? This fiber, so I'm integrating over the fiber above x, and psi, when restricted to this fiber, takes that into the original fiber. And this is C1 function. So how do you measure the surface area, or just Hausdorff measure of this object here? We have a parameterization of that object by phi. And by area formula, if you integrate the Jacobian of that parameterization, which will be exactly this quantity here, okay? If you integrate Jacobian of that parameterization on this affine set, that will give me the surface area of this object here. And therefore, the interior integral will give me the quantity equal to, okay, so this will be projection onto k tilde, and this will give me exactly the m minus n dimensional measure of the image of psi. But the image of psi of this vertical line is the original fiber of my original function. Above what point? About phi of x, which is just that z. And this is relevant to k, right? Because the fiber we restricted to k tilde, so its image is restricted to k. And now this thing we put outside the integral because it only depended on x and not on y. dln of x. Okay, now comes the last u substitution formula. What I'm integrating here is, okay, here we have k tilde and we have its projection. Okay, I am integrating a function. Okay, if you have a, so here is the image Rn, here is Z, which is phi of x. Phi is this bi-Lipschitz map going that way. The U substitution for integrals is saying that if I have a map from here to R, then to integrate hz, dlnz, I can integrate using the change of variable z equal phi of x. Then this will be h of phi of x. Then comes the Jacobian of phi, so d phi of x, dln x. Over now the pre-image, which will be this projection onto k tilde. Right, that will be the u substitution again for integrals, and phi is particularly nice. C1 in fact on an open domain containing this projection. In this, now when you compare this formula to this quantity here is h of phi of x, and this is determinant Jacobian. So it's this side here. Therefore, this is just integral over the image of projection h m minus n f inverse of z intersected with k d h n z. And this is the right hand side in the Coarea formula that we were seeking. So let me go back and show you what we actually computed. We started with integrating the Coarea factor over k. We did a transformation to k tilde neighborhood. In the k tilde neighborhood, we did the Fubini's theorem. The vertical fibers via psi parameterize the original fibers. So integrating that determinant of the vertical map gave us the measure of the fiber. That's this quantity here. And then another application of change of variables in integration landed us here. I must mention that going from this to all of our n doesn't change anything, because if you integrate over stuff outside the image of the projection, because you intersect with k here, it automatically gives you 0. So it doesn't matter if I increase the domain of integration to beyond basically phi of the projection of k tilde part. So this intersection with k or k tilde automatically catches them. And this is the Coarea formula for the subset K. As we mentioned, a countable union of K's exhausts all of the regular part of our domain, where rank is equal to n. And then we had sort theorem to take care of the non-regular or critical part of our sort. And by additivity of the formula, we have concluded the proof of the Coarea formula. Okay, so some computations, but of course such a difficult result, such a general statement, and we cannot expect much simpler proof. But anyway, I want to give an example where we will see indeed how this proof is actually working, although it's quite geometric enough. But in the example that I'm about to give, we don't have to deal with measurable sets, so everything will be an open domain and things are simpler. What we want to do is we want to go back to integration in polar coordinates. In my video 2, I actually showed you how it follows from the Coarea formula. So what you do is you have as your Rm, you have R2. And then you want to integrate a function by first integrating over the circles. So you have to give a description of circles as fibers of some map. And that map happens to be the function that goes into R1, where f of a vector is just the length of the vector. And these will work in arbitrary dimension. So this notation is perfect. So this will be root of x squared plus y squared if this vector is xy. Okay, gradient of f, or derivative of x at x tilde, is x tilde over absolute value of that for every x other than 0, from which it follows that Coarea factor of d of x is just norm of this, because it's just a column vector or row vector multiplying with transpose and taking derivative, and then square root is just back to the norm of the vector, and this will be equal to 1 whenever x is other than 0. So by the Coarea formula, Lebesgue measure of a measurable set. So here we're talking about what's going on. Any set A like this is integral of the Coarea factor. It's equal to integral of 1, but now Coarea factor, okay, let's not write it, is equal to 1. So then there's integral of the Coarea factor, and then by Coarea formula this will be on R1, which is from negative infinity to positive infinity, but this f will never pick up any negative values by being an absolute value. This will be H1 measure of fiber of f intersected with A, and dl1 of z. So z and the fiber above it. But it's just better notation to switch to r, because this image of f is exactly the radius of the circle. So that we know from the Coarea formula. And it's just a nice formula that just compute the L1 measure of the length of the fibers you get within A, and then add those length up, you get area. So you measure area by measuring length. But we did this, we went to this example to illustrate how the proof above functions. The way it worked was, of course, because of the implicit function theorem that we had. So here we have fibers, and then we said that locally you can find this C1 diffeomorphism, which corrects these fibers into vertical lines, so that f, after this change of coordinate system, becomes a projection. So this becomes just phi of one variable. So what will be our psi in this example? Do you have a guess? Think about it. What will be this fiber correcting map psi that goes from one copy of R2 to another copy of R2, so that these fibers of f, which are just circles, of course my picture sucks here, will correspond to this under the C1 change? And the answer is, if you want to really think about it, it's time for you to pause and do so. in this new core R2, we use the new variable names. It's just an artificial change of names. In reality, it's just a map between two copies of R2. But there is meaning in this R and theta. So this becomes R cosine of theta or sine of theta. You can confirm that away from 0, which is a problem point, if you pick a neighborhood, a small neighborhood, away from 0, which is the critical set of the function, incidentally. So remember, this psi exists only on the regular set, where the rank of the derivative is maximum. Here, rank of derivative being 1 just means that the derivative is non-zero. And here we see that it's true for every x other than 0. At 0, the derivative doesn't exist, so there's even not a point of asking whether we can do this. Anyway, so away from 0, this transforms to a new region, probably very different shape. And then the fibers are exactly vertical. If you freeze R, so let's say you freeze R0, and then this will be, actually you have to restrict to something between negative pi and pi. So any period that doesn't, whose length is not, any interval whose length is not equal or more than 2 pi. We know what happens, because then this region goes and, sorry, so this goes all the way back. This becomes too much of an open set and it comes back onto itself. So you have to avoid that. So you can take your open region as like this, but not too close that they touch and overlap. So when you freeze your R0, the fiber here, let's maybe use red, the fiber above this corresponds to this fiber, which is the circle at radius r, not all of it, of course. Oops. The part that is within this, that's funny now, within this neighborhood A or K that you picked. And yes, so that's a very concrete example of how the proof worked and why it worked. So hopefully it helps explain some parts. Yeah, with that, I'll let you go. Thank you for watching, and please subscribe if you have not yet, because there's even more fun coming up in this channel. Probably I'll have 2 or 3 more videos on this subject, Coarea formula, and then I'll continue with something else. But meanwhile, please do comment, ask questions. If you would like to see a certain topic covered, please do mention that. But anyway, have a good day.